Good day. I'm J Wildberger, and this is the second of a series of videos on the foundations of mathematics. Please have a look at the first video if you haven't already done so. Last time we introduced the most important objects in mathematics, the natural numbers. We said that a natural number was just a string of ones. So the sequence of natural numbers looks just like this. First one is 1, the next one is 1, 1, the next one is 1, 1, 1, and then 1, 1, 1, 1, 1, and so on. We also mentioned the standard names for the first few of them, 1, 2, 3, 4, 5. But to carry on, naming them requires the Hindu-Arabic numeric system, and we don't have that yet. So it's safer for us to think of a general number like this as just 1, 1, 1, 1, 1, 1, a string of ones. Alright, so let's go back in time, maybe 100,000 years, to a waterhole in Africa. We might imagine a 10-year-old boy there who's been sent by his tribe to count animals. And he sees a bunch of buffalo and antelope, let's say. Buffalo are these squares, and the antelope are the triangles. And he's pretty good at counting. He's figured out a way of counting things. He has a piece of bark, and on the bark he makes little scratches, one for each of the animals that he sees. So for example, counting buffaloes, here's how he would do it. There's one, there's one, there's one, 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 one. Of course he has to make sure not to repeat. Counting antelopes, the same. There's one, 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 1, 1. So he goes back to his village with his piece of bark, and he shows the elders these marks, and they can sense how many buffaloes and antelopes there are. They may not have a name for these numbers like we do, but still it gives them a very good idea of what's at the waterhole. Now suppose his father asks him, how many animals are there in total? Why don't you go back and count them all? Our young boy, who's rather clever, realizes that he doesn't have to go back to the waterhole to count them all, because he has counted the buffalo and he has counted the antelope. And he can use the numbers that he has obtained to find the number of all the animals. And he does that by what we call adding those two numbers. How do we do that? Well, he just copies the first one. 1, 1, 1, 1, 1, 1, 1, 1, 1. And then he adds the second one. 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. That then is the total number of animals at the waterhole. And he hasn't had to go back to the waterhole to do it. He's a very clever young boy. This is an example of the most important operation in mathematics. The operation of taking the sum of two numbers. So here's our official definition. The sum of numbers n and m is the combination of the strings of ones. By combination, I mean you just put them together in the obvious way. Concatenate them in computer science language. And we write that sum as n plus m. So our young friend back in the African savannah 100,000 years ago, if he kept playing with numbers, let's say he did, he would probably discover certain facts about this addition operation. And the main facts are that it's, first of all, commutative. N plus m is the same as m plus n. Let's illustrate. So here is 5 plus 2. Concatenate them, we get this string here. On the other hand, here's 2 plus 5. Concatenate them. And these two numbers are the same. We can get that by matching them up one by one. Why is it true? Well, it's almost obvious. If you combine two things, it doesn't matter in which order you combine them if you're just interested in the total number. Or another way of thinking about it is in terms of inverting them. If we take this pattern here and flip things over, the total number of ones hasn't changed, but we've gone from that pattern to this pattern. That's the commutative law of addition. Another main law is the associative law, which concerns three numbers. we agree that addition is an operation that only takes two numbers and gives you another number. So if we have three numbers, there are two possibilities for how to combine them. We can combine k and n first, and then add that to m. Or we can take k and add it to the sum of n and m. For example, k is 2, n is 3, m is 4. Here's 2 plus 3 plus 4, so that's 5 plus 4, giving us this string. On the other hand, 2 plus combination 3 plus 4 is 2 plus this combination, which gives us this string. And why are these always the same? If we think of the strings like this, for example, concatenate the first two and then concatenate with the third, it gives us the same as if we concatenate the second and third and then concatenate with the first. The resulting configuration is the same. A minor law, which we'll just mention, that the successor operation, which we talked about last time, can be rewritten now as n plus 1. Those are the laws of addition. Now things get more complicated when we introduce multiplication. This is a new level of difficulty. Here's a motivating example. We have 3 boxes, say, and in each box there are 4 circles. So there are 4 circles in a box. And we have altogether 3 boxes. We'd like to know how many circles are there altogether. Well, it's a matter of combining 4 plus 4 plus 4. So we think of this, we're going to write it like this. This is 3 times 4. And that for us means 3 groups of 4. Or a way of thinking about that is we're going to replace each of the ones in this first string with a copy of the second number. So that first one is replaced by a 4. The second one here is replaced by another 4. And the third one is replaced by another 4 to give us this resulting string. So we say that the product of numbers n and m is the string formed by a copy of m for every 1 in n. So the laws for multiplication are these ones. The commutative law, n times m equals m times n. The associative law, k times n times m equals k times n times m. And then there are 2 additional laws called the distributive laws that connect addition and multiplication. And they are k times n plus m is equal to k times n plus k times m. And we introduce an important notational device. We say that we're going to allow ourselves to rewrite this expression without these brackets in the form k times n plus k times m. So our convention is that multiplication takes precedence over addition. In other words, whenever you see a multiplication sign, you have to do that first. And then there's another distributive law in the other direction. K plus n times m equals k times m plus n times m. The laws on these 2 pages are the most important laws in all of mathematics. In fact, they are far more important than almost anything else. They're important because they're simple and because their effect in everyday life is so profound. All of mathematics uses these laws directly or indirectly all the time. We need to understand why these laws are true. And we need to understand it in a way that doesn't involve any abstract symbolism or gobbledygook. We need to be able to explain it in everyday English using only the notation and the conventions that we've established so far. So I'm going to leave this as an exercise to you for now, which we'll talk about in our next video. Right? But please write out proofs, in other words, reasons for these laws. I've given you reasons for the addition laws. Laws for the multiplication and distributive laws. See if you can write out in a way that our 10-year-old friend in the African savannah 100,000 years ago would understand. Alright, so we'll talk about that in our next video. I'm J Wildberger. I hope you join me. Thanks for listening.